Okay, this is the screencast for section 8.2, sampling distributions of the mean of X. Have somebody display this up on the board for the entire class to watch. You'll have to swipe on your computer screen to the left to get to, let's say, I think it's devices, and then you're going to project. And my computer will already be paired, but you guys will have to, whoever decides to do it on their computer will have to add a wireless display and then look for one that says room N148, and you have to pair it with the code and make sure it's all turned on and stuff like that. But it would be best if one person could project this up on the board. Okay, so here we go. The distribution that would be formed by considering the value of a sample statistic for every possible different sample of a given size from a population. So we're talking about sampling distributions. We're talking about doing lots of samplings and then finding out what is the mean going to be. So in this case, the sample statistic is the mean. So X bar is going to be the mean. Right, so this, let's see, last week we talked about the fish example, and I believe there were 20 fish, but now we're only going to talk about 5 fish in the pond. And so they've randomly chosen 5 fish. The length of the fish are given below. So we'll keep all the population size small so that we can figure out all the different possibilities. So first of all, what's the mean and the standard deviation of this population? Well, to find that out, you can put it into your calculator and let your calculator do all the work for you, but you should get the mean of 7.84 with the standard deviation of 3.262. So the mean length is 7.84 inches with a standard deviation of 3.262 inches. So if we look at this, remember we were catching fish and taking the average size of them. So this time let's find all the sample size 2. So that means we're going to draw 2 fish at a time. So if we start with 6.6, we want 6.6 and 11.7, 6.6 and 8.9, 6.6 and 2.2, 6.6, 9.8. Then 11.7 with 8.9, 2.2 and 9.8, and you kind of get the idea here of all the different patterns. So that's where all of this is going to come from. They've just paired those numbers and found the mean. So here's all of our sample means. And now the question we're really going after for this section is, what if we take the mean of the means? So what if we were to sample all of this and then take those means? Well, we would get 7.84. Hey, not a coincidence that it is the same as what it was when we just took the entire mean of the 5 fish. What about the standard deviation? Ooh, that's changed. Is it smaller or larger? Well, you're going to notice that the sample standard deviation is going to be smaller than just the standard deviation of all of the data together. And we just compared that it's going to be the standard deviation stays the same, but the mean stays the same, the standard deviation will get smaller. So now what happens if we up it to choosing 3 fish at a time instead of 2 fish? So let's list all the possibilities here. So here's all the ways you can grab 3 of those 5 fish and find the mean. So any guesses on what the mean of the means is going to be, the sample mean? So the sample mean is going to be, again, 7.84. That will stay the same. So when we had 2 fish, the sample distribution, standard deviation, was smaller than the standard deviation of the entire population. So what happens now if we're choosing 3 fish instead of 2 fish? Well, the standard deviation got even smaller. So the more numbers we pick, the smaller it causes the standard deviation to be. So we've got some general properties we need to talk about. So one of the first things is to talk about the mean of the sampling distributions will always equal the mean of the population. And the sample size, as the sample size increases, the standard deviation of the sampling distribution decreases. So again, as we sample more and more numbers, the standard deviation is going to get smaller and smaller. So kind of an inverse relationship there. Okay, so some general properties. Rule number 1, we just said it. The mean of the sample has to equal the mean of the population. And rule number 2, the standard deviation is going to equal the standard deviation of the sample is going to equal the standard deviation of the population divided by the square root of the number of items you're taking at a time. And what's in green is real important. It says this rule is exact if the population is infinite and approximately correct if the population is finite and no more than 10%. So we talked about this. No more than 10% of the population is included. So our last example had 5 fish. Oh, there we go. 5 fish. But we were collecting 3 at a time. That's actually 60%. So what we were using, we couldn't actually use a sample size or a population that small with a sample size so large. And that's what this is talking about. Note that the previous fish pond examples in the standard deviation formula was not correct because the sample size were more than 10% of the population. So let's take a look at another example. The paper mean platelet volume in patients with metabolic syndrome and its relationship with coronary artery disease. Includes data that suggests that this distribution of platelet volumes of patients who do not have it's a late night tonight. Metabolic syndrome is approximately normal with a mean of 8.25 and a standard deviation of 0.75. So that's our important information there. And so there it looks on a normal bell-shaped curve. And it says we can use Minitab, which is a computer program, to generate 500 random samples of choosing 5 at a time. So it's just our same information. We're going to do 500 random samples. We're going to choose 10 at a time, 20 at a time, and 30 at a time. So here are those 5 graphs. This is where we're choosing a sample size of 5, a sample size of 10, a sample size of 20, and a sample size of 30. And each of these is being done 500 times. And this is the resulting data. So what do you notice? Couple of things, 2 things actually. You should notice their center is all around the mean. Every single one of these has the center around the mean. And then the other thing you should notice is as the sample size is increasing, so as this is getting larger, the standard deviation is getting smaller. So what do you notice about the standard deviations of these histograms? The larger sample size we have, so we're up to 30, has these very teeny tiny standard deviations. So rule number 3 is when the population distribution is normal, the sampling distribution of X bar is also normal for any sample size n. Remember, less than 10%. Okay, so in the paper, is the overtime period in an NHL game long enough? Gave data on the time in minutes from the start of a game to the first goal scored for the 281 regular season games from the 2005-2006 season that went into overtime. The density histogram for the data is shown below. So the first thing you should recognize about this is that this graph is skewed to the right, and it even says it in bright red, strongly positively skewed, and it has a mean of 13 with a median of 10. So using Minitab, we're going to generate again 500 samples of the following sample sizes from this distribution. So just like we did before, they're going to do a sample size of 5, a sample size of 10, 20, and 30, and they're going to draw each of those 500 times. And something amazing is about to happen. Notice what kind of shape is taking place in all 4 histograms. I hope that you see that it is approximately normal. And in fact, when you get to n equals 30, so 30 games sampled at a time, it is approximately normal. And this is going to be key for us to be able to figure out future confidence intervals. How confident can we say the mean is going to be between this number and that number? But it does need to be approximately normal. They all have the same center of approximately 13, and as you go higher and higher for the sample size, the standard deviation gets smaller and smaller, and then it takes the shape of an approximately normal curve. So property 4, the central limit theorem, also known as the CLT. When it's sufficiently large, the sampling distribution of x bar is well approximated by a normal curve, even when the population distribution itself isn't normal. So we just saw an example of that where it was very positively skewed to the right, but when we started sampling it, the sample distribution ends up being approximately normal. And so here you can see, here's our population curve, how it's skewed off to the right. If we draw a sample size of 4, it gets a little bit more normal, and then a sample size of 16 gets a lot more normal. It's very tall and skinny, but it is approximately normal that way. So, how large is sufficiently large anyway? So the CLT, remember the central limit theorem, can safely be applied if n exceeds 30. So here's our mark. If we can have 30 samples or more, 30 being sampled or more, remember that it still has that 10% rule. We're going to be able to apply the central limit theorem. So one more example, a soft drink bottler claims that on average cans contain 12 ounces of soda. Let X denote the actual volume of soda in a randomly selected can. Suppose that X is normally distributed with the standard deviation of 0.16 ounces. 16 cans are randomly selected, and the soda volume is determined for each one. So the X bar is the resulting sample mean soda. So if the bottler's claim is correct, then the sampling distribution of X bar is normally distributed with a mean of 12 and then a standard deviation of 0.4, because again, this is the population and this is the sample size. So when you figure out this formula, you should have in those 16 cans a mean of 12 and a standard deviation of 0.04. So what is the probability that the sample mean of soda is going to be between 11.96 ounces and 12.08 ounces? So we have to find the z-scores for these two things, and they just did a real quick transformation of the z-score. Instead of being divided by the standard deviation, they are replacing the standard deviation of the population with the sample divided by the number in the sample. And when you click through this, we're going to actually find the probability on your blue charts from -1 to +2. And because we're finding the in-between, this is when we're going to subtract those probabilities. And so we would have an 81.85% chance of getting a can that has a volume between 11.96 ounces and 12.08 ounces. Our last example, I believe, talking about this is a hot dog manufacturer asserts that one of its brands of hot dogs has an average fat content of 18 grams per hot dog with a standard deviation of 1 gram. Consumers of this brand would not be disturbed if the mean was less than 18 grams. So they'd be okay as long as it has less than 18 grams of fat. but they would be unhappy if it exceeds 18 grams of fat. An independent testing organization is asked to analyze a random sample of 36 hot dogs. It's good that it's 36 because it's more than 30. Suppose the resulting sample mean is 18.4 grams. Does this result suggest that the manufacturer's claim is incorrect? So let's go back and look at what their claim is. A hot dog manufacturer asserts that one of its brands of hot dogs has an average fat content of 18 grams per hot dog with a standard deviation of 1 gram. So let's test this to see if it's true or not. Since the sample size is greater than 30, we can do the central limit theorem here. So the distribution of x is approximately normal with a mean of 18 and a standard deviation of 0.1667. So suppose the resulting sample mean is 18.4 grams. Does this result suggest that the manufacturer's claim is correct? So remember, the claim was it has an average of 18 and a standard deviation of 1 gram. And of those 36 hot dogs, we found a mean of 18 and 0.1667. So really what we're doing is trying to find the probability that we're going to have a hot dog over 18.4 grams of fat. So to do that, let's get a z-score. We get 2.4, and because we want above, we're going to subtract it. So 0.82% of the time, you're going to have a hot dog that has more than 18.4 grams of fat. So the sample mean of 18.4 is large enough to cause us to doubt that the manufacturer's claim is correct. Because it's such a small number that we're going to get more than 18.4, we have to doubt that it's going to be correct. All right, and our last part here is let's explore what happens in distributions of sample proportions. Have students perform the following experiment. By the way, we're looking for p-hat, which is also a statistic. Toss a penny 20 times and record the number of heads. Calculate the proportion of heads and mark it on the dot plot on the board. Well, because I'm not there today, we're not going to do a dot plot on the board, but I am going to show you we've actually done something like this, and we're going to be able to answer this question. What shape do you think the dot plot will have? And after we look at the shape, we are going to have your homework assignment. So let's go back and look at that shape. And we'll keep the ink. And let me go back in, and I'm going to the Google Docs where we've flipped some pennies before. So I believe just last week or something we had a is it real, trying to determine if flipping the coins and counting the number of times it landed on heads was going to be a normal distribution, to try to figure out who was telling the truth and not telling the truth. So when we look at our data, what does that look like to you? Does it look like it's approximately normal? Does it look like the average number, the mean is going to be right there in the middle? And I'm hoping that you're saying yes, that it is that way, that you're seeing a mean. Oh, but I can't draw on it, I guess. All right, so I hope you're able to get through this video. Sorry I couldn't be there today. I will return on Friday and answer any and all of your questions that you may have.